idea behind them, the logic behind them. So one of the primary jobs of statisticians is to estimate characteristics of populations. We've already talked about that. That's been kind of the beginning of a couple of sections now. We're trying to estimate characteristics of a population. Those are parameters. Parameters are characteristics of a population. Okay? What proportion of students drive to school? What is the average weight of a teenager? How much money per week do students spend on eating out? I mean, you can ask any question you can ask. You can come up with probably a way to gather information about it and estimate it. Okay? So to make these estimates, statisticians will select a sample from the population of interest and study the members of the sample. Okay, so if you want to know about a population, you take a sample and you see what happens with that sample. But there's something called sampling variability, which we talked about at the very beginning of the last unit. Sampling variability is where all of you will go out. If you went out and asked 100 people the same question, how many times do you eat fast food per week? Okay, you'd all come back with a different proportion number out of 100 that ate fast food that week. Wouldn't you? Some of you might have the same number. You know, some of you would have different numbers. Okay, so that's sampling variability. All of your samples will have different answers. Okay, it doesn't make any of you right, it doesn't make any of you wrong. They are just different. Okay, just like people are different, we just accept that. There's variability in the samples that we collect. So it is possible that our estimates are wrong. Okay, we could be wrong. Okay, so in general there are two types of estimates that can be made. Point estimates. All we have made so far are point estimates. We go out, we collect a sample, we write down the data from our sample. That is a point. A point is a single thing, one number, one statistic. Okay? A point estimate is a single statistic, a single stat. Okay? One piece of information. Okay? And now we're going to move up and we're going to find interval estimates. Interval estimates is a range of a statistic. We're giving, now I know you think range and you think domain and range from algebra. It's kind of like that. A range means we're giving more than one choice. We're allowing ourselves some room. So an example, okay, let's say I went out and I sampled people and I said, on average, how many times do you eat out per week? Okay, or I mean, that might be a little bit difficult to do a proportion out of 100. You know, do you eat at McDonald's? You know, yes or no? That could be a very simple question. Go ask 10 people, do you eat at McDonald's, yes or no? You either eat there or you don't eat there. Okay, so I get a single value. Let's say I find that 5 out of 10 students ate at McDonald's. That is a single statistic. Okay, what we're going to do is we're going to say, okay, well, that single statistic, I'm trying to find out, when I ask the question, do you eat at McDonald's, yes or no, I want to know overall, like everybody, do you eat at McDonald's? But I'm only going to ask a small portion. And so that's probably a wrong answer, isn't it? Probably wrong. So what I'm going to do is I'm going to calculate, and we'll get a formula for it today, a range around 5/10, 0.5. So I got that 50% of people eat at McDonald's, okay? But that's probably wrong. Okay, but it's probably kind of close to the right answer if I did a good sample, if it was random, if it was less than 10% of the population, okay, and n times p and n times q would have to be greater than 10. I mean, obviously I'll have to do a bigger sample size if I really want all the conditions satisfied. But I'm going to give myself a range of statistics. So I'm going to say, well, how far away could I go from 1/2 and still be within a reasonable amount? How far away can you go from something? 3 standard deviations. Now we're going to limit that. You're right, 3 standard deviations and then you become an outlier. We're actually going to make it a little smaller and say we're only going to go 2 standard deviations. So a point estimate is a single statistic. A range of intervals is where we say, okay, well, I'm going to go 2 standard deviations above and below and give myself a range. So a range, an interval estimate, would be something centered around 1/2, say maybe 0.4 to 0.6. And this is not an ordered pair, this is interval notation from math. The first number means I'm saying, instead of just saying 50% of people eat at McDonald's, I'm going to say between 40 and 60% of people eat at McDonald's. Do you suppose that if I say between 40 and 60% of people eat at McDonald's that I've actually captured the true number of people that do? It's more likely that I've captured it compared to just saying 50%. Okay, so what we're going to be doing today is we're going to be gathering one statistic and making it into a range, a confidence interval. I am confident that the true proportion of people that eat at McDonald's falls between 40 and 60%. Okay, it's called a confidence interval because it gives you more confidence in being able to say, I think that this is a range of values that represent the true value of this. So, a point estimate, we just kind of talked about both of those. A point estimate is a single number that represents our best guess for the population parameter. It's called point because it represents a single point on the number line. For example, based on a recent survey, we estimate that 61% of young adults favor Social Security reforms. Okay? An interval estimate is a range of plausible values for the parameter. Instead of just saying a single number, we just give it a range. So it is called an interval estimate since it represents the interval on the number line, an interval on the number line. For example, based on a recent survey, we estimate that between 58 and 64% of young adults favor Social Security reform. Okay, they're usually more confident in saying a statement like that range rather than the 61% before. Now notice, where is the 61% in this interval from 58 to 64? Where is it? It is always the middle. The point estimate, the statistic you gather, is always the middle of the confidence interval. And in fact, you take the 61% and you simply add and subtract the 3%. We need to learn how to calculate that 3%. 2 standard deviations away, above and below. Okay, using an interval estimate greatly increases the probability that we're correct. For example, if I predict the high temperature tomorrow will be between 0 and 150 degrees, I have great confidence that I will be correct. Although it actually, probably for tomorrow, it might not even be close because it's probably going to be below 0. Okay, so, I mean, is this big of a range? Giving a range about values, I mean, you're like, oh, that's easy. I could just say between 0 and 100. I'm pretty sure I'm confident I'm going to get between 0 and 100 on this test. Okay, well, that's not really, you're not really trying. You're just throwing out all the values, okay? A range is, you know that your single statistic isn't probably correct, so you're going to allow yourself a little room for error. So the 0 to 150, if the weatherman came on every day and said that, you'd be ticked because you wouldn't know how to dress. I'd be mad. I always kind of dress based on the weather a little bit, or at least put on a coat that is appropriate. So of course this interval won't help me pick my clothes in the morning. There is a trade-off between confidence and usefulness. Okay, I'm 100% confident, or the temperature tomorrow will be between negative 100 and positive 100 degrees, but it's not useful. Okay, so we want the confidence interval to be useful. So making point estimates, which statistic should we use? Okay, there are 2 things to look for when choosing a statistic to estimate a population characteristic, a parameter. The statistic should have no bias and low variability. Now, quite honestly, you aren't going to have to worry about choosing a statistic. You're always going to be told which statistic to use. But the way they came up with these, the more common ones, is because these are unbiased. And we talk about unbiased statistics. Unbiased statistic. An unbiased statistic is a statistic with a mean value equal to that of the population characteristic being estimated. In other words, its sampling distribution is centered in the right place. So, for example, in the textbook problem, some unbiased statistics, unbiased, they gave you lots of answers near the actual 100, okay? Twice the median actually was a good one. Twice the mean. These are just some examples. The min plus the max. And Q1 plus Q3. Okay, those are actually all they've been tested and proven to be fairly unbiased statistics, okay? But those aren't easy. I mean, they're simple to calculate, but they're not the common ones that we use. They're unbiased since their sampling distributions were centered in the right place. In other words, the estimates weren't consistently too high or too low. Okay, because I know some of you saw in your statistics, you know, they're always above 100, or some of them were really low, or their range was just huge. All right, so top of the next page, some examples of biased statistics would be, well, the range is pretty biased, and the maximum is pretty biased. The mean plus 3 standard deviations is also biased. It's always going to give you estimates consistently too high and too low. It's not going to give you anything in the middle, okay? If you unless you're trying to estimate the maximum, okay, but usually you're trying to estimate the middle of the data. All right, why are these biased? Centered in the wrong place. And it should be obvious why the range, or especially the max and the mean plus 3 standard deviations, is centered in the wrong place. You want it centered at the mean, okay? The mean plus 3 standard deviations is always going to be high. All right, so given a choice between several unbiased statistics, which should we use? The one with least variability. Okay, we'll just put it at that. The one with least variability. Again, you aren't going to be choosing the statistics. You will be told which statistic to use as your point estimate every time. So sometimes, occasionally, it's a biased statistic is preferred if it has much less variability. In other words, if it's constantly, it might be biased, it might be a little too high, but it's always it's got a very small range. All right, so in the next 2 chapters, we're going to be focusing on 2 unbiased statistics. So again, I said, you aren't going to have to pick them. A lot of what we talked about just there was if you were a statistician, you know, and you were trying to estimate something about a population and you knew it required some statistic that hadn't been calculated yet. They invent new statistics every day, by the way. All right, so the 2 things we're going to use is the sample proportion p hat and the sample mean x bar. And today we're talking about the sample mean. So making interval estimates. Because of the variability inherent in sampling, our point estimates will rarely be correct. After all, different samples will yield different estimates. And although a point estimate may be our best single guess for the value of a population parameter, is certainly not the only possible value. Thus, the statistician will usually report an interval of plausible values where your point estimate is the center for the population parameter based on the sample. This interval is called a confidence interval. Confidence interval. Using a confidence interval gives a much better chance of correctly estimating the parameter. So the logic of confidence intervals, a little bit. Okay, so they're saying the distance from P to P hat is the same as the distance from P hat to P. Well, what's the difference between P hat and P? P hat is my sample value, P is the true value, okay? So it's saying the distance is the same. You know, here's P, the true proportion, here's P hat. It's saying the distance between those two is the same either way you look at it. So 95% of all samples will give a sample proportion within 1.96. Now, isn't 1.96 pretty close to 2? Okay, 1.96 standard deviations of the population proportion P. Now, this comes from the normal model. What percent of data is within 2 standard deviations of the true value? 95%. That's why it's called a 95%. Okay. Now, technically, it's only 1.96 standard deviations that's within 95%. Okay. Technically, 95% is within 1.96. We round it to 2. Okay. So 95% of all samples will give a sample proportion P hat within 2 standard deviations of the population proportion P, assuming the distribution is normal. Therefore, 95% of all samples, the population, in 95% of all samples, the population proportion will be within about 2 standard deviations of the sample proportion. When the distribution of P hat is normal, the 95% confidence interval for a population proportion P this is the formula right here. Well, there's actually 2 forms of the formula. You need to memorize this one I'm putting a box around right now. That's the one you will get on the AP Stats exam.